So, Bayes theorem, we're looking to use some new information to update the probability of an event. So, what is the probability of an event A given that we now know B has happened? And so we can use the Bayes theorem formula. The probability of A given B is the probability of B given A, which we know, and the probability of A, which we also know, and the probability of B, which is the normalization factor, which we can either it's given or we can calculate that. So we have a scenario here of um, about the Twilight movie, and we have someone by the name of Rory, and he watched the movie, and we want to know what is the probability that Rory is a fan given that he watched the movie, right? So that's the probability of A being a fan given that he did watch the movie. And so these are the information we have. The probability of being a fan is 0.2. So 20% of the population are fans. And then the probability of B given A, that is the probability of having watched the film, given that you're a fan, it's 60%. And then the probability that you watch, given that you're not a fan, that was 0.05 or 5%. And so we can find this B probability, the probability of having watched the film, whether you are a fan or not. So that will be the probability of having, having watched the film, be given that you're a fan, times the probability of being a fan, plus the probability of having watched the film, given that you're not a fan, times the probability of not being a fan. So we find this product and that product, and we sum them all together, and so we get 0.16. So the probability of not having watched a film is 16%. So now that we know the B probability here, we can substitute that into this formula and find the probability of A given B. So that would look something like this. We would have our probability of being a fan, given that you watched, is going to be the probability of having watched the film, given that you're a fan, times the probability of being a fan, divided by the probability of having watched the film, which we determined here. So 0.6, the probability of being a fan, times 0.02, the probability of being being a fan. This is the probability of being a fan given that you watched, and that so the product of that divided by the probability of having watched a film. So we get that to be 0.75 or 75% chance that Rory is a fan. So we can look at it here again, and there are the say 50 people, and 40 of those people are not Twilight fans, but 2 of those 40 actually watched, and then we have 10 here who are Twilight fans, and of those 6 watched, or 60%. So that's what that would look like. And so essentially, if we looked at that, if we only cared about those who watched the film, it would be these 6 here and these 2 here, which would be amounting to 8. And of those 8, 6 of them were fans. And so there is a 75% chance, or 6 or 8% that Rory was a fan. We have another example here. Now, this is a rare disease testing. So we have this disease, and it is extremely rare. 0.01% of the population has it. And there's a test for the disease, and the test is 99% correct, whether you have the disease or not. All right, so let's set up our probabilities, our prior and our likelihood, and our normalization. So prior probability of having the disease, 0.001. The probability of testing positive, we don't know that. The probability of having the disease, given that we test positive, that's what we're trying to find, right? So the probability of testing positive is the probability of B. So the probability of A given B is going to be the probability of B given A times the probability of A divided by the probability of B. So the probability of sick, given that you test positive, is going to be the probability of positive, given that you're sick, times the probability of sick, all divided by the normalization. And so we can set that up with the code P underscore sick. Sick is the probability of being sick, 0.0001. And of course, then the complement of that, the probability of not sick, is going to be 1 minus that probability. So that's our prior probability. And then the likelihood probability. This is the probability of testing positive given that you are sick, 0.009. And the complement of that, probability of not testing positive given that you're sick, would be 1 minus that. So now we can set up our new evidence or normalization factor. That is the total probability of testing positive. And so that's going to be the probability of testing positive given that you are sick times the probability of being sick. And that is going to be added to the probability of testing positive given that you are not sick times the probability of not being sick. So we have all of our different probabilities set up, and so now we can use that. We have the prior, which is the probability of sick. We have the likelihood, which is the probability of testing positive given that you're sick, and then we have the normalization, which is the probability of a positive test. And we have the lovely Bayes Theorem formula function here, which takes prior likelihood norm, where it's the prior times the likelihood divided by the norm. So we would run that. That's our function. Now we can substitute our values in here, and we can get the probability that a person will actually test the probability that you are sick given that you test positive with the disease. So that is a 0.098%. Very low probability. And it makes sense because the probability of the disease in the population is 0.01%. So very, very rare. Now, if the probability of the disease were higher, so instead of being 0.00001, it's now 0.02. So now we have the new probability for the disease. Everything else is the same. The probability of the test being correct, the true positive, is 0.99, and then the probability of test being testing positive if you're not sick, which is the true negative rate, it's going to be 1 minus the probability of not being sick. And so again here the normalization factor is the same as before. We can run that, substitute that into our function, our new priors, the same likelihood and the same normalization. Well, the normalization changes because we have a new probability of being sick. So we put all that into the equation and we get this is our new probability of being sick if we test positive, because the probability went from 0.0001 to 0.02. So quite a change in the prevalence of the disease. So if we were to now, instead of having a different disease prevalence, we have a different test accuracy. And so the test is now 99.9% correct, whether you have the disease or not. And so here we have our probability of being sick. And here is the probability of testing positive given that you're sick. And conversely, the probability of testing positive given that you are not sick in this case is going to be 1 minus that. And similarly, as we had above, the probability of testing positive, whether sick or not sick, is going to be the product of testing positive times probability of sick, probability of testing positive given that you're sick, times the probability of sick, and the probability of testing positive given that you're not sick, times the probability of not having the disease. And so we set up our sick prior, our positive sick likelihood, and our positive normalization. And so the probability that you are sick, we put those into our function and we get a 9.8% chance that we are actually sick. So now we see that the test is gone from 99% accurate to a 9.9%. So whereas before we had a probability of 0.98%, now with the more accurate tests it's gone up, where probability of being sick has increased 10 times. And so we can do the same thing if we wanted, instead of going through all of the setting up all the priors, we can simply find the positive, the denominator, and we can substitute the sick prior here, and then this positive likelihood that we had, as well as our normalization factor. That's a kind of quicker way of doing this. Now, if we took the test and it was positive, and we decided, you know what, we want a second opinion, we took a second test, not really second opinion, but we took the test twice, and it came up positive both times. So now the incidence of the disease is the same, and the accuracy of the test is the same. So we have 0.99. But now our probability, actually, our new likelihood is going to be the square of the probability of testing positive given that you're sick. So we have a new likelihood here. The prior stays the same, and now we also have a new normalization, because in this case we're going to be multiplying the probability of being sick by this new uh, probability of testing positive, and similarly we'll be multiplying the probability of not being sick, but the new probability of not being sick, given that we test positive twice. So we have all of that. We substitute into our formula, our function, and we have the probability of being sick now. It's almost 50%. So definitely, getting that second test showing positive has certainly increased the the likelihood that we are sick. And so that is the idea of how we use the